In the last lecture, we looked at steady-state balance, that is, the ability to control posture in a fairly predictable and unchanging set of conditions. Today we'll be looking at reactive balance and proactive balance. Reactive balance involves the ability to recover a stable posture following an unexpected perturbation, and proactive balance involves the ability to control balance in advance of a potentially destabilizing voluntary movement. Reactive and proactive balance control have some defining characteristics. Reactive balance is compensatory, that is, it occurs in response to information about unexpected postural disturbances. Information about postural disturbances is detected by the visual, vestibular, and somatosensory perceptual systems. Reactive control occurs in response to rapidly occurring perturbations. Even though rapid responses occur rapidly, they can be modified by experience. Proactive control is anticipatory, that is, it's organized in anticipation of a particular disturbance to balance. Proactive control is predictive of disturbances. It's triggered centrally before the onset of a voluntary movement. Proactive control acts to prevent destabilization of posture during limb movements. As with reactive control, it can be modified by experience. Here we see a useful schematic for understanding the roles played by reactive and proactive balance control. This schematic starts in the top left-hand corner with the intention to perform a movement. Here we see that an intention to raise the right arm has been formulated. This intention is then turned into a central command. The motor system turns the central command into a limb movement. The physical movement of the limb that results creates a postural disturbance. This postural disturbance, if it isn't accounted for, could destabilize the balance of the body. Let's start by looking at proactive balance control, shown in the green parts of the schematic. Proactive balance control starts with a copy of the central command that generated the limb movement. The copy of the central command is turned into feed-forward information about how the planned movement is expected to disturb the balance of the body. The feed-forward information about the expected disturbance is translated into anticipatory adjustments. These adjustments are organized to counteract the expected perturbation. Let's now look at reactive balance control, shown in red. Unlike proactive balance control, that is organized before planned movement that has even started, reactive balance control happens after the movement has been performed. Reactive balance control starts in the top right of the schematic, with the postural disturbance. Raising the arm will shift the center of mass of the body anteriorly. If this shift in the center of mass is not anticipated, it will create an unexpected pull upon the body, pulling it forwards. This disturbance to balance will be registered by vestibular, visual, and haptic perceptual systems. These perceptual systems are able to detect information about the nature of the balance disturbance. This feedback information can be converted into reactive adjustments. In the first part of today's lecture, we will develop our understanding of reactive balance. In reactive responses, sensory feedback about an unexpected disturbance to balance is used to organize a coordinated muscle activation that acts to stabilize the body. Reactive responses are functional, that is, they are adapted to the situation that they occur in. Postural responses are adapted to the characteristics of the perturbations that are experienced. For example, a reactive response will be organized to effectively oppose both the direction and the magnitude of the perturbation experienced. Postural responses are also adapted to the biomechanics of the situation. These include the musculoskeletal geometry and intersegmental dynamics of the movement of the body. Lastly, postural responses are also adapted to the environment that the action is performed in. For example, how the body is oriented relative to the surrounding surfaces. The next characteristic of reactive responses for us to understand is response delays. A reactive response is evoked between 80 milliseconds and 100 milliseconds after the onset of a perturbation. An additional 50 milliseconds can be required for force to build up in the recruited muscles. Response delays also depend upon the state of the body when the perturbation occurs. Specifically, the ability to organize an action that can effectively counteract the effect of a postural disturbance depends upon the current posture of the body, the current velocity of body motion, and the integrated effects of the forces that are currently applied to the body. All of these different sources of delay can mean that a reactive response may not be observed for as long as 500 milliseconds after a perturbation. A useful way to understand reactive balance is through the concept of strategies. A movement strategy describes a particular way of organizing movement with respect to a particular motor control goal. Reactive postural response strategies describe different ways of organizing movement in order to counteract unexpected perturbations. We will start by looking at the strategies that have been identified for reactively maintaining balance in the anterior-posterior direction. That is, maintaining balance in the face of perturbations that are occurring in an anterior or posterior direction. The first strategy for us to consider is the ankle strategy. With an ankle strategy, an unexpected perturbation to the body is counteracted by modulating ankle torque. In this strategy, the head, arms, trunk, and legs move as a single unit, and the orientation of the body is controlled by changing the anterior-posterior position of the center of pressure under the feet. The hip strategy involves hip flexion and extension. This strategy can be used to shift the location of the center of mass of the body. The hip and ankle strategies for reactive balance have the same basic form as the ankle and hip strategies we previously discussed when we were talking about steady-state balance in the last video. The ankle and hip strategies are referred to as fixed support or feet-in-place strategies, since the base of support for these strategies remains unchanged. Next, we see the step strategy. This strategy works by increasing the base of support in the direction in which balance is threatened. By taking a step forward, the base of support extends forward and therefore allows the center of pressure to extend much further forwards. Lastly, we have the reach-to-grasp strategy. By reaching forward and grabbing hold of part of the environment, a new point of physical contact with the environment is created. Just as with the step strategy, this increases the base of support. The step strategy and the reach-to-grasp strategy are both termed change in support strategies. So, when are different reactive balance strategies likely to be used? The ankle strategy is typically employed when the support surface is firm, and the magnitude of the experienced perturbation is moderate or small. An example of this strategy in action is in the context of the task of standing up on a train. Here, you're standing on a firm surface, and most of the time the perturbations you're going to experience are going to be quite small and can be counteracted by changes in ankle torque. Next, we have the hip strategy. The hip strategy is typically employed when the surface that the feet are in contact with is narrowed or compliant, and when the magnitude of perturbation is larger. When standing on a train, if you get a jolt, if rather than experiencing the small perturbations, there's a jolt in the train, this could induce the use of a hip strategy. Here we see a woman balancing on a log. You can see that the curved surface of the log means that only part of her feet are in contact with the ground at any particular moment in time. This reduces the contact area, and it reduces the functionality of the ankle strategy. It makes it much more likely that a hip strategy will need to be employed. Here we see a kid standing on a bed. The surface of the bed is compliant, and this surface and this surface is compliant because the surface is soft and will deform under pressure. Other examples of compliant surfaces include a sandy beach or a rocky hillside. In these cases, the surface is compliant because the structure of the surface will give way under pressure. Compliant surfaces create situations in which changes in the location of the center of pressure under the feet do not have reliable consequences. The unstable ground surface produces inconsistent ground reaction force vectors. So when are we likely to observe change in support strategies? Change in support strategies are typically employed when fixed support strategies are inadequate for recovering stability. Even though we would expect a change in support strategy to be needed when the center of mass falls outside of the base of support, a change in support strategy is sometimes used when the center of mass is still within the base of support. For example, with the people standing on the train, it's far more socially appropriate to grab onto a railing for balance than it is to use a hip strategy. There are some general beliefs regarding reactive balance strategy use. Small balance perturbations usually result in the use of an ankle strategy. As perturbations get larger, there is a switch to a hip strategy, and finally to a stepping strategy. We can see this visualized here. The black dot in the center represents the center of mass. It has an initially stable location well within the base of support. We see that the ankle strategy is given an area. Small unexpected perturbations will unexpectedly shift the location of the center of mass. As long as these perturbations do not take the center of mass outside of the ankle strategy region, then an ankle strategy will be an adequate choice for maintaining balance. As perturbations get larger and larger, we see that the hip strategy will be needed, and eventually a stepping strategy will be needed. The schematic shows how we expect strategy to change as a function of perturbation magnitude. This particular schematic represents normal stance, that is, when both feet are in contact with a firm ground surface. The next general belief about strategy use is that the way in which strategies are used will vary depending upon the context. Here we see the schematic of the strategy switches we might expect if a person is standing on a narrow beam. This is basically the same context as standing on a fallen tree that we looked at in an image a minute ago. If the support surface is a narrow beam, then the region where the ankle strategy will be useful is dramatically reduced. This means that we will see a hip strategy being used in response to much smaller perturbation magnitudes. We've just been looking at strategies for maintaining balance in the anterior-posterior direction. Let's now look at a strategy for maintaining balance in the mediolateral direction. The hip load-unload strategy works by changing the center of pressure location under the feet in the mediolateral direction. In this strategy, a perturbation is counteracted by unloading weight off one limb and onto the other limb. In the two graphs shown on the left and the right of the image of a person's legs, we can see the percentage of weight that is being supported by the left and right limb. When a person is standing symmetrically, we would expect approximately 50% of body weight to be supported by each limb. The blue line in each of these graphs shows when the limb is supporting 50% of body weight. If we look back and forth between these two figures, we can see that when one limb is supporting more than 50% of body weight, the other limb is necessarily supporting less than 50% of body weight. In the graph at the bottom, we can see the changes in center of pressure that accompany these weight shifts. This graph shows the mediolateral position of the center of pressure under the feet. The green line shows the midpoint between the feet. When body weight is just distributed symmetrically across the legs, then we expect the center of pressure to be located between the two feet. Remember, the center of pressure is the location of the ground reaction force vector. Right at the start of this recording that we're seeing in these time series here, body weight is shifted onto the left limb. We see that shifting the weight of the left shifting weight onto the left limb shifts the center of pressure towards the left foot. When we reduce the percentage of body weight that's supported under one limb, we allow gravity to pull the body towards the less loaded side. We can use this as a strategy for counteracting perturbations. The hip load-unload strategy relies on the action of hip abductors and adductors. For example, if you adduct one leg and abduct the other leg, a mediolateral shift of the pelvis will result. This will shift the weight of the body, and this action can be used to counteract perturbations. Now that we've introduced the main reactive balance strategies, let's look more closely at them. To do this, we need to look at some research specifically studying reactive balance. Experimental investigations of reactive balance frequently use an apparatus like the one shown here. In this apparatus, the participant stands on a solid plate that can be rapidly shifted via the hydraulic pistons acting underneath it. In this particular apparatus, the ground can be shifted forwards or backwards, and it can be tilted up or down. Let's start by looking at an experiment that used the moving platform apparatus to study the organization of an ankle strategy. In this experiment, the experimenters produced an unexpected posterior shift of the platform that the participant was standing on. This shift pulled the feet backwards and pitched the body forwards. This resulted in a forward sway of the body. Here we see the muscles that are recruited in order to counteract this particular perturbation to balance. In the EMG time series, we see clear recruitment of the paraspinal muscles, the hamstrings, and the gastrocnemius. The function of the paraspinals and the hamstrings in this reaction is to maintain the hip and the knees in an extended position. In other words, the actions of these muscles act to keep the body being relatively rigid. The gastrocnemius functions to increase ankle plantar flexion torque, and therefore to slow and then reverse the forward sway of the body. The ankle strategy represents a particular way of organizing a response to balance perturbations. A noticeable characteristic of this strategy is that muscles are recruited in a specific order. We see that distal muscles are recruited first, followed by proximal muscles. We just looked at the response to a backwards platform shift. Let's now look at the response we observe following a forwards platform shift. This shift pulled the feet forwards and pitched the body backwards. This results in backward sway of the body. Here we see the muscles that are recruited to counteract this particular perturbation to balance. In the EMG time series, we see clear recruitment of the abdominal muscles, the quadriceps, and the anterior tibialis. The function of the abdominal muscles and the quadriceps is to maintain the hip and the knees in an extended position, and, as before, to keep the body relatively rigid. This rigidity means that changes in ankle torque can act upon the body as a whole. The anterior tibialis functions to increase ankle dorsiflexion torque, and therefore to slow and then reverse the forward sway of the body. This dorsiflexion torque shifts the center of pressure anteriorly. Again, we see a distal to proximal recruitment of muscles. Now let's look at a slightly modified version of the experiment, where the experiment is now designed to look at a hip strategy. The first thing to notice in this version of the experiment is that the participant is forced to stand on a narrow beam. This means that only part of the feet are in contact with the platform. A narrow beam was used to ensure that a hip strategy was used rather than an ankle strategy. In this experiment, the experimenters produced an unexpected posterior shift at the platform. This shift pulls the feet backwards and pitches the body forwards. This results in a forward sway of the body. The hip strategy involves backward motion of the hip. This motion shifts the center of mass of the body posteriorly and acts to keep the center of mass over the base of support of the feet. Here we see the muscles that are recruited to counteract this particular perturbation to balance in this particular set of circumstances. In the EMG time series, we see clear recruitment of the abdominal muscles and the quadriceps. The function of the abdominal muscles and the quadriceps is to flex the hip. We just looked at the response to a backwards platform shift. Let's now look at the hip strategy response to a forwards platform shift. This shift pulls the feet forwards and pitches the body backwards. This results in backward sway of the body and forward motion of the hips. Here we see that the paraspinal muscles and the hamstrings are activated to extend the hip and to bring the pelvis forwards. This shift in the position of the pelvis shifts the center of mass of the body anteriorly and acts to keep the center of mass of the body over the base of support provided by the feet. At this point, we have a pretty good basic understanding of reactive balance strategies. Given this foundation, we can begin to appreciate some of the subtleties of reactive balance. An important functional part of reactive balance control is that reactive balance responses are adapted to the characteristics of the perturbation. To begin to understand this, we can look at how the velocity of an experienced perturbation affects the observed postural responses. Based upon what was known about ankle and hip strategies at the time, Runge et al. Hypothesized that ankle strategies would be primarily used when low-velocity perturbations were experienced, and that hip strategies would be used when high-velocity perturbations were experienced. To test this hypothesis, Runge et al. Used a moving platform apparatus to study the effect of anterior-posterior platform perturbations with velocities ranging from 5 centimeters a second to 47 centimeters a second. Runge et al. Recorded the activation patterns of multiple muscles known to be relevant to ankle and hip strategies. In this complex figure that we're looking at here, we can see the EMG time series for each muscle that's believed to be relevant to these strategies for 5 different velocity conditions. To understand these plots, let's just focus in on the moment on the trapezius recordings that I've highlighted in blue. Within this blue area, we see 5 lines. The line at the bottom, labelled A, shows the activity of the trapezius after the lowest velocity perturbation. We see that this line is almost entirely flat, suggesting that the trapezius is not recruited in response to low-velocity platform perturbations. The line at the top, labelled E, shows the activity of the trapezius after the highest velocity platform perturbation. In this condition, we see clear activity. The lines in between the top and the bottom lines are the intermediate velocity conditions. Now that we understand this figure, we can start looking at the results of this study. Contrary to expectations, subjects did not show a switch from using an ankle strategy at lower perturbation velocities to using a hip strategy at higher perturbation velocities. Instead, participants were found to recruit ankle muscles at all tested velocities, and to recruit hip muscles at some critical threshold. We can see this here. In the activation patterns of the gastroc muscle that I've highlighted in red. Notice here that we see a clear activation of the gastroc immediately following the perturbation, and that the activation occurs in all of the different lines. That is, it occurs in all of the different velocity perturbation conditions. Now, If we look at the activation of the quadriceps that I've just highlighted in green, we see that this particular hip strategy muscle is not recruited during low velocity perturbations, but it is recruited for higher velocity perturbations. These results support the conclusion that reactive balance can involve a combination of blending of hip and ankle strategies. As well as studying muscle activation patterns, Runge et al. Also calculated joint torques at the hip and at the ankle. Here we see time series of ankle torques for the different perturbation velocity conditions. In this plot, the thinnest lines are for the lowest velocity conditions, and the thickest lines are for the fastest velocity perturbations. What we see here is that following the perturbation that is taking place at 0 seconds in the plot, ankle plantar flexion torques are created in all conditions. We also see that there's a steady increase in ankle torques with increasing perturbation velocities. This is consistent with greater forces being needed to counteract the increasingly stronger perturbations. Here we see the corresponding time series of hip torques. We see that hip torques are minimal for the lower velocity perturbations, but when we get to a perturbation velocity of about 32 centimeters per second, we see a sudden and dramatic increase in the hip torques that are produced in response to the perturbation. As before, these results suggest that an ankle strategy is used at lower perturbation velocities, but that a combination of ankle and hip strategies is used at higher perturbation velocities. The next quality of reactive balance for us to consider is how reactive balance responses are adapted to the direction of the experienced perturbation. To study this, Henry et al. Used a moving platform apparatus that could shift the platform beneath participants' feet in any direction. Henry et al. Studied multiple directions of platform perturbation and looked at the responses to these perturbations in multiple muscles. To understand these results, we'll first look at a part of them. We'll first look at data for one muscle, the left tensor fasciolate. Here we see the EMG time series for the left tensor fasciolate in response to 12 different directions of perturbation. At the top, we see the response to the anterior platform shift that induces a backward sway of the body. We can see that the EMG activity we get in response to this perturbation is minimal. We're seeing minimal activity. On the right-hand side, we can see the response to a rightwards platform shift that leads to a leftward sway of the body. Here, in contrast to the plot we just looked at, we see a high level of activity in the left tensor fasciolate. Taken together, all these recordings represent a continuum of muscle responses, capturing the responses to all directions of perturbations. We can represent this continuum of responses using a plot like this one. Using this circular plot, we can capture the amount of response that we see for each direction of perturbation. For example, we just created a red dot at 0 degrees. At 0 degrees, we have the response to a leftward body sway. This is the biggest response, so we're going to place the red dot at the maximum distance from the center of the circle. 60 degrees in the plot corresponds to a body sway that is mostly backwards, but still has a component of leftward sway to it. Here we see an EMG response that is about 1/3 the amplitude of the largest response. So at this point, with this point, we position the point 1/3 of the way out from the center. If we do this for all of our data, for all of our different directions, we create a line that captures the amount of activity in all directions. Now that we understand how to create this particular type of plot, and how we're creating it for the left tensor fascial latae, let's go and look at the data for all of the muscles that were investigated in this study. Here we see all 12 of the perturbation directions that were investigated in this study. Here we see the plot that was developed on the previous slide containing the data for the left tensor fascial latae, and we also see a line representing the activation and the response of the left rectus femoris. You should immediately notice that the two lines that are created for the responses of these two muscles are almost identical. This suggests that we have two muscles that are organized to respond the same way as a function of the direction of perturbation. Here we see two other sets of muscles. These new two plots are organized so that the muscles that have similar response profiles are placed in the same plot. From these data we can see that there are three distinct response profiles. There is one group of muscles that is recruited maximally when the perturbation direction is 0 degrees. There's another group of muscles that's recruited maximally when the perturbation direction is around about 325 degrees, and there's a final group of muscles that is selectively recruited for a perturbation direction around 60 degrees. Remember, what we're looking at here is just the response of left-sided muscles. The take-home message of this research is that muscles are groupable by having the same responses to different directions of perturbations. The authors of this paper conjecture that these data reveal three distinct muscle synergies that each have specific directions of endpoint force. Endpoint force refers to the creating of a force in the environment that acts in opposition to the direction of a perturbation. On the previous slide, we used the term synergies. In motor control, a synergy is a technical term. A synergy is a group of muscles that are constrained to act together as a functional unit. The concept of synergy is an important one. Fundamentally, a synergy acts to organize the many muscles of the body into functional subunits. This organization simplifies the demands placed on the central nervous system that would otherwise have to individually control each muscle. One of the basic characteristics of a synergy is that muscles are organized to act as a functional unit. Here we see the paraspinal muscles, hamstrings and gastrocnemius all working together to counteract the forward sway of the body. This synergy has certain characteristics. It involves specific muscles, the muscles are recruited in a specific order, and the activation of each muscle is timed relative to the activation of the other muscles in the synergy. There are different ways of understanding exactly what a synergy is. The easiest and simplest theory of what a synergy is assumes that a particular muscle can only belong to one synergy, and that each of the muscles within a synergy have the same gain on them. The word gain is used to refer to the amount of activation. A high gain refers to a high level of activation, a low gain refers to a low level of activation. In the image here, we have a visual representation of this theory. We see that there are three synergies: Synergy 1, Synergy 2, and Synergy 3. Synergies 1 and 2 each have 4 muscles in their organization. Synergy 3 just has 2 muscles. A given muscle does not appear in more than one synergy. The 0 and 1 at the bottom of each plot of each synergy represent the amount of contribution of each muscle. 0 represents no contribution, and 1 represents a full combination. A full contribution. As you might expect, the assumptions of this traditional theory have not stood the test of time. Today, I'll introduce you to 2 modern theories of the nature of synergies. The first theory we'll look at is based upon the non-negative matrix factorization approach. The term non-negative matrix factorization simply refers to the particular statistical method that sits behind the theory. What we're interested in is what this theory reveals to us about the nature of synergies. In this theory, a muscle is able to belong to more than one synergy. The non-negative matrix factorization approach also proposes that within a synergy, an individual muscle has a unique or fixed weighting factor to represent its contribution to the action of the overall synergy. In order to understand synergies based upon the non-negative matrix factorization analysis, we want to work through a simple example. In this example, we will assume that there are just 3 muscles that are being organized into synergies. These muscles are M1, M2, and M3. In this theory, a functional movement depends upon multiple synergies working together. Each synergy is going to be symbolized in this explanation with the letter W. The organization of each synergy is defined by the relative contribution of each muscle. If a particular muscle does not contribute to the synergy, then the activation level is going to be set to 0. If it contributes maximally, then the activation level is going to be set to 1. The next part of the theory concerns scaling coefficients. Scaling coefficients are symbolized in this explanation with the letter C. Scaling coefficients are used to capture the relative contribution of each synergy to a movement. As we will see in a second, the scaling coefficient multiplies all of the elements of the synergy by a constant to determine the specific level of activity from each muscle. Let's look at this visually. To understand this diagram, start by noticing that we have 3 muscles at the bottom: muscle 1, muscle 2, and muscle 3. And in the middle of the diagram, we have 2 synergies, W1 and W2. Finally, at the top of the diagram, we have 2 scaling coefficients, C1 and C2. We can see that scaling coefficient C1 is related to synergy 1, and scaling coefficient C2 is related to synergy 2. If we make C1 larger than C2, then synergy 1 will make a larger contribution to the organization of the movement. When we look at synergy W1 on the left, shown in red, we see that we have 3 boxes. Inside each box we have symbols representing the relative activation levels for each muscle. These activation levels are given the symbol lowercase w. The subscripts on these lowercase w's identify which synergy we're looking at and which muscle is being activated. For example, with W subscript 1, the first one identifies that we're looking at synergy 1, and the second one identifies that we're looking at muscle 1. In the case of W subscript 1-3 in the third box, on the right side, we are looking at synergy 1 and the relative activation of muscle 3 in that synergy. The activation of a muscle by a synergy is going to depend upon the combination of the relative activation level of the muscle and the scaling coefficient of the synergy. If we look at the red arrow going from synergy 1 to muscle 1, the amount of recruitment of this muscle is going to be determined by the relative activation level, W subscript 1, multiplied by the scaling coefficient. A key feature of this theory is that a particular muscle can be part of multiple synergies at the same time. Now that we have an initial grasp on the theory of synergies based upon the non-negative matrix factorization analysis, let's look at how this theory gets applied to understanding balance stabilization. The analysis we're going to look at was developed to understand the reactive postural responses of cats. In this research, The cat stood on a platform that could be shifted in any direction. At the bottom of the screen, we can see the long list of muscles that were investigated in this particular study. We're going to be looking at a study of cat balance because it provides the easiest way to understand the theory. The lessons that we'll learn from this data have been shown to apply to human balance, although we won't review the application of non-negative matrix factorization to human balance in this class because it's a lot more difficult to understand. The analysis of the responses of the 12 different muscles during the 16 different directions of perturbation revealed 4 different synergies. If we look at synergy W1, W subscript 1, we can see that the relative activation levels of the muscles are illustrated with the red bar. As before, a full red bar signifies the largest possible relative contribution. For synergy W1, we see that the gluteus medius has the largest possible contribution, whereas the biceps femoris has almost no contribution. Now that we've identified the synergies, we need to ask how these synergies are combined via the scaling coefficient to produce a particular movement pattern. Here we see the scaling coefficients associated with each of the 4 synergies. For the moment, let's just focus on the red line that shows the scaling coefficient for synergy W1. In this graph, on the y-axis, we see that the coefficient ranges from 0, which would mean no contribution, to 1, which means a maximal contribution of the synergy. On the x-axis, we have perturbation direction. What we see then is that the contribution of synergy W1 to reactive balance varies with a specific function of perturbation direction. Specifically, what we're seeing here is that synergy W1, W subscript 1, is scaled to make its largest contribution for a perturbation direction of around about 260 degrees. In contrast, we see that synergy W3 is scaled to make its largest contribution for a perturbation direction of around about 180 degrees. In sum, when we look at each of these different scaling coefficients, what we're seeing that each of these 4 synergies is recruited for specific directions of balance compensation. The implication here is that reactive balance synergies have a specific direction to them. In other words, each synergy is related to an organization of muscles that, when activated, will create a distinct endpoint force between the limb and the support surface that will counteract a particular direction of perturbation. The final component of this theory that we need to understand is how the level of activation of a specific muscle is determined. In this theory, the activation of a specific muscle depends upon that muscle's recruitment by the various synergies. For example, a couple of slides back, we saw that the gluteus medius is only involved in synergies W1 and W3. We also saw that the gluteus medius makes a maximum relative contribution in synergy 1, but only about a 25% contribution to synergy 2. Based upon this, we can plot the relative contributions of the gluteus medius to each synergy. The red line shows the contribution to synergy 1. The red line is maximally scaled. The green line shows the contribution to synergy 2. The green line, correspondingly, is scaled to 25%. The black lines in the plot show the activation level of the muscle. This level is determined by adding the contributions that the muscle makes to each synergy. So, for example, if we look at the 200-degree perturbation direction, we see that synergy 1 is requesting about a 75% activation of the muscle, and that synergy 3 is requesting about a 20% activation of the muscle. This produces an overall muscle activation of 95% of max. there are some general takeaway points from the non-negative matrix factorization theory of muscle synergies. First, synergies are limited in number. From both animal and human data, a limited number of synergies, 5 or 6, has been shown to be sufficient to explain the muscle activity that results from perturbations from a whole bunch of different directions. The next takeaway point is that synergies are functional. The muscles synergies that have been discovered in this research tend to produce forces that possess consistent global biomechanical functions. These biomechanical functions tend to be preserved across a range of postural configurations. The synergies of reactive balance have clear biomechanical functions. We can see that each synergy relates to a particular way of controlling endpoint force. We can see this represented graphically in the figure. The red arrow shows the force that's created by synergy W1. This force pushes into the ground and helps maintain the upright posture of the body. It also has a lateral component. The green arrow, in contrast, shows the force that's created by synergy W3. This force also pushes into the ground, but is directed posteriorly, such that it can be used to counteract posterior sway. There are 2 more takeaway points regarding qualities of modern synergies. The first takeaway point is that muscles in synergies are globally functional. By this we mean that muscle activity is consistently evoked in response to center of mass destabilization, as opposed to local joint angle changes. The second takeaway point is that muscles in synergies are degenerate. The term degenerate refers to the idea that muscles can belong to more than one synergy, and that within a synergy, an individual muscle has a certain proportion of the contribution. So what is the value of a theory of synergies? To understand why synergies are an important concept, we need to look at how synergies fit into the organization of motor control. Here we see a diagram that includes various aspects of motor control organized around the goal of regulating the posture of the body. Right at the top of the diagram, we see that we have the higher levels of the central nervous system. At this level, we are setting our goal of regulating the posture of the body. This goal sets a combination of sub-goals. These include the sub-goal of holding the body in an upright anti-gravity posture, and the sub-goal of maintaining balance. The primary role of synergies is to translate the abstract sub-goals, such as the sub-goal of supporting the weight of the body, and translate it into patterns of muscle recruitment that realize that particular function. In the diagram, we can see that the abstract sub-goal of weight support is connected to synergy 1, and that synergy 1 is in turn connected to multiple muscles. We also see that the sub-goal of balance is connected to synergies 2, 3, 4, and 5. Notice in this diagram that each muscle can receive inputs from multiple synergies. The resulting patterns of muscle activation generate joint torques at the hip, the knee, and the ankle. These torques in turn generate endpoint forces. Endpoint forces refer to the forces that each foot is exerting on the ground. Right at the bottom of this diagram, we have multisensory inputs. These refer to information detected by the various perceptual systems about the body's position and movement in space. This information is used to help organize how appropriate synergy combinations can be recruited. For example, if an unexpected perturbation to balance occurs, then the various perceptual systems will detect information about the nature of that perturbation. This might include the direction of sway of the body and the velocity of body sway. This sensory information can be used to change the scaling coefficients of various synergies. This way, those synergies that are associated with creating forces that will oppose that particular direction of perturbation will be recruited. This diagram allows us to understand one of the key functions of synergies. Synergies help to simplify the task that's being faced by the central nervous system, the task of controlling many, many muscles in the body. Without synergies, the higher levels of the central nervous system would need to control 12 muscles in this diagram, and much more in reality. Instead, we have an organization that allows for 12 muscles to be controlled by varying the values of a much smaller number of synergies, here 4 or 5 in our diagram. Now let's turn and look at a second modern theory of synergies. This is a theory developed by Mark Latash. In this theory, Mark proposes a new definition of the term synergy. In its original definition, a synergy is a group of muscles that are constrained to act together as a functional unit. For Latash, a synergy is something that organizes the sharing of a task among a set of elemental variables. Notice that we've replaced a set of muscles in the original definition with a set of elementary variables in this new definition. We will flesh out what we mean by elemental variables shortly. For Latash, a synergy is something that ensures adaptive covariation among elemental variables, with the purpose of stabilizing a certain performance variable. An example of a performance variable would be the ability to keep the center of mass within the base of support. Let's unpack the key concepts in Latash's theory. Elemental variables, or EVs for short, are the basic functional units of action that are controlled by the central nervous system in this theory. Elemental variables are proposed in contrast to other potential basic variables, such as joints or muscles. What makes elemental variables different from joints or muscles is that elemental variables are functionally independent from each other in the absence of task-specific control. For example, try and flex your middle finger. When you do this, you'll notice that your ring finger also flexes. This shows us that the joint motions of your middle finger and ring finger are not functionally independent. Because the middle finger cannot be independently controlled, we say that it's part of an elemental variable, as opposed to constituting its own elemental variable. In contrast, flexion of the index finger can be considered to be an elemental variable, since it can be moved to a large degree independently. With the concept of elemental variables in hand, we can now look at how a synergy is organized. Elemental variables are used to form different synergies that stabilize a performance variable. A synergy, then, is a set of elemental variables that are organized to produce a particular functional outcome. Here we see two synergies, A and B. As with the non-negative matrix factorization theory, we see that a particular elemental variable can play a role in more than one synergy. The last key concept that we need is adaptive covariation. The concept of adaptive covariation proposes that the functional contribution of synergy is maintained or stabilized by changes in the magnitude of the elemental variables that comprise it. In this diagram here, we see synergy A twice. The big blue arrow at the top is signifying that the output of this synergy is the same on the left and on the right. What we notice, though, is that the particular combination of elemental variables is not the same. What is happening is that the elemental variables have been combined in different ways in order to produce the same functional output. We'll develop this idea further on the next slide. In this theory, synergies are functional units. They are organized to create a particular functional outcome. The simplest way to understand the concept of adaptive covariation is through the idea of an uncontrolled manifold, or UCM. And the simplest uncontrolled manifold we can create has two elemental variables. The plot here shows the UCM, or the uncontrolled manifold, for the task of creating a steady force with two fingers. Here we see a person playing a guitar. In order for the chord being played to sound right, a constant force must be created through the combined action of the index finger and the middle finger. We can treat the force created by each finger as a separate elemental variable in this example. To understand how this task is performed, we can plot the force generated by the index finger on the x-axis of our graph and the force generated by the middle finger on the y-axis of the graph. To perform this task successfully requires that close to 10 newtons of force is generated. The key to understanding adaptive covariation is understanding that the required 10 newtons of force can be generated in multiple ways. For example, the index finger can produce 10 newtons of force, while the middle finger produces no force. Or the middle finger can produce 10 newtons of force, while the index finger produces no force. Or the index finger can produce 6 newtons of force, while the middle finger produces 4 newtons. If we come up with all possible combinations of forces, we will create the thick blue diagonal line. If you create any combination of forces with your fingers that falls on this line, then you will perform the task successfully. So this particular performance variable will be optimized. If we were to measure the forces created by the index and middle fingers in this task, and we were to create a data point for each observed combination, we would observe a cloud of data points that looks something like this, the green dots. Here we see that the participant does not always perform the perfect combination of forces, which is why some of the green dots do not land exactly on the blue line. What we do see, though, is that the various combinations of forces tend to fall along the line. We can summarize the data here by drawing an ellipse around the data. If the person is performing the task well, then the ellipse will be aligned to the UCM, and it will be narrow. According to Latash, adaptive covariation is a hallmark property of functional motor behavior. It's easy to appreciate why we would expect functional behavior to be organized like this. If we are performing the task of holding the chord on the guitar for a long time, then one of our fingers, the weaker one, might get fatigued. And when it does so, it would start generating less force. In this case, we would want the other finger to take up the slack. In a different scenario, if we change the posture of the arm, it may become easier to produce force with the index finger. In this case, we might expect the middle finger to take on a greater contribution. Latash refers to this type of functional organization with the principle of abundance. The principle of abundance proposes that the central nervous system organizes its elements such that they all compensate for each other's spontaneous errors, as well as for the potential errors that may result from unpredictable forces acting from the environment. This theory has some implications for understanding the nature of motor control. Remember, synergies are an intermediate level of functional organization in motor control. Higher levels of the central nervous system will recruit synergies, and the synergies will take care of the details of organizing how the elemental variables are coordinated. Given this, an implication of Latash's synergy theory is that as long as you stay on the line of the uncontrolled manifold, a higher level of controller will not need to intervene in the motor control. Now that we understand the basics of Latash's theory of synergy, let's look at how this theory can be used to evaluate the functionality of motor control. Latash and colleagues proposed a technique called uncontrolled manifold analysis. UCM analysis is used to quantify the strength of a functional relationship between the elemental variables in a synergy. We can use our guitar task to think about this. The task, again, is to create a combined force of 10 newtons with both fingers. Here we see 4 very different performances of the task. In each case, an oval, as we talked about on the previous slide, is used to show the shape of the cloud of data points that we observed when the task was performed. In the top right plot, we see that the ellipse is aligned to the uncontrolled manifold. This means that a synergy has been organized. In the top left, we see more of a circle rather than an oval. This means the combinations of forces that we're observing do not really seem to care about maintaining the intended output. In this case, we do not have a synergy. We can measure the strength of a synergy in these two cases. We can do this by measuring var UCM and var ORT. var UCM, var underscore UCM, is the length of the oval in the direction of the uncontrolled manifold. Var ORT is the length of the oval in the direction that's orthogonal to the direction of the uncontrolled manifold. If we look at the ratio of var UCM and var ORT, we can measure how well the data cloud is constrained by the uncontrolled manifold. In the top right, the ratio of var UCM and var ORT is 1. This means we don't have a synergy. In the top left, the ratio of var UCM and var ORT is greater than 1. This means that we do have a synergy. In the bottom left plot, the ratio of the var UCM and var ORT is much greater than 1. This means we have a very strong synergy. In the bottom right plot, the ratio of var UCM and var ORT is close to 1. This means that this is a weak synergy. This is an interesting case here, because in this case, the task is actually being performed effectively. But what we're not seeing is adaptive covariation. Now that we've taken the time to learn Latash's synergy theory, let's consider how it can be used to understand reactive balance. Up until now, we only considered an uncontrolled manifold with 2 dimensions, or elemental variables. The reason that we looked at such a simple example is because it's possible to visualize the UCM easily in this case. When you have a large number of elemental variables, it's no longer possible to visualize the uncontrolled manifold. In this situation, the analysis becomes entirely mathematical. Schultz et al. Used Latash's synergy theory to study the way in which reactive balance is organized. The performance variable that Schultz considered was the anterior-posterior position of the center of mass of the body. Schultz then calculated the uncontrolled manifold that involved the motions of the joints of all of the joints of the body. Schultz calculated the uncontrolled manifold that corresponded to all possible combinations of joint angles that were equivalent with respect to the task of producing an average pre-perturbation position of the center of mass. The analysis that Schultz performed revealed that when a person is recovering from a loss of balance, that person tended to re-establish the pre-perturbation center of mass position rather than the pre-perturbation joint configuration. In other words, Schultz demonstrated that there is adaptive covariation of the joints with respect to the task of controlling the center of mass. A simple but theoretically important implication of these findings is that what we have here is a direct demonstration of the fact that the center of mass is a key variable, a key performance variable that's being controlled by the central nervous system during postural control. I want to finish up our consideration of reactive balance strategies by looking at how postural response strategies postural response synergies are refined and tuned. The terms refining and tuning are referring to processes of adapting the synergy to changing demands. As we've learnt from Latash's synergy theory, postural synergies are not fixed, stereotypical reactions. Rather, postural synergies can be reorganized to be adapted to a change in demands of the task and a change in the environmental situation. A simple example of the adaptation of postural synergies can be seen in the following way. If a person experiences repeated balance perturbations that are all of the same type, then over time we will observe a change in muscle activity that acts to make the response more efficient. For example, if you're standing on a train and all of the perturbations that you're experiencing are causing a moderate amount of backward sway, you're able to adapt to that situation and develop synergies that are fine-tuned to counteract that particular type of perturbation. The second piece of evidence that reveals how postural responses can be refined and tuned comes from the study of response strategies. We know from our earlier discussions that it's possible to switch postural response strategies as needed. It's also possible to alter the particular blend of strategies that's being used so as to be adapted to the current situation. The simple example of this that we considered earlier was an increase in the use of a hip strategy when standing on a narrow beam. A straightforward example of the process of refining and tuning a postural response can be seen in an experiment by Horak and Nashner. Horak and Nashner looked at the reactive balance of young healthy subjects. The group of subjects was shown to use a predominantly ankle strategy when standing on level ground. These participants were then stood on a narrow surface, and the response strategy quickly shifted from an ankle strategy to a hip strategy. With practice, somewhere between 5 and 15 trials, less postural sway was observed in the responses, and a lower amplitude of muscle activation was seen. In other words, the participants quickly increased the efficiency of the reactive balance in the new situation that they were placed in. In the final part of this lecture, let's develop our understanding of proactive balance control. In proactive or anticipatory balance control, the central nervous system organizes forces based upon anticipation of what an intended task requires. Here we see a person picking up a box. We can see that they believe that the box is full of books. Based upon this expectation, the central nervous system will organize an action that is adapted to the task of lifting a heavy box. The central nervous system will also organize a response to the anticipated perturbation of lifting and holding this box upon standing balance. Let's now look at a very simple example of proactive balance control. In the experiment depicted here, participants perform the very simple action of initially standing with both feet on the ground, and then when a signal light comes on, they lift up their right foot behind them. From the outset, participants know the action they need to perform when they see the signal light come on. The researchers here recorded the activity of the right rectus femoris, the left rectus femoris, and the right biceps femoris, both leading up to and during the execution of the action. When we look at the graph, we see three lines that represent the muscle activities of the three muscles that are being recorded. We also see a white vertical bar in the plot. This white vertical bar shows the region of time leading up to, in preparation for, the onset of the action. This plot identifies the muscle activity that occurs in anticipation of the movement. In other words, the movement only began at the end of the preparation phase, but we're seeing muscle activity within the preparation phase. Here we see the EMG time series from this research zoomed in, seeing it in more detail. Looking at this data, we can see that there is a particular order of recruitment of the different muscles. First, we see an increase in activity of the rectus femoris in the stance limb. The rectus femoris creates an anti-gravity extensor torque. In other words, this muscle helps to keep the knee extended and to stop the knee from collapsing under the weight of the body. The function of the early activity of the rectus femoris is postural. It is anticipating the need to load the full weight of the body on the left leg so that the right leg can be unloaded and moved. Next, we see activity in the muscles of the right leg. These muscle activities are used to stabilize and to move the right leg. The lesson from this data is that we tend to see postural activity anticipating voluntary movement. In other words, in a voluntary movement, we should expect to see muscles that ensure stability of standing posture being activated before we see muscle actions associated with performing the intended movement. Let's look at a second example. In the task studied in this research, the participant is simply asked to raise their right arm up in front of them. In order to perform this movement, what we see is a particular sequence of changes in muscle activation levels. We initially see the activation of postural muscles, coloured in orange. These activations are used to compensate in advance for the destabilizing effects of the target arm movement. We then see the activation of the muscles that are involved in flexing the shoulder. As in the last study, proactive balance stabilization is organized before the intended movement is performed. The activation of postural muscles that we are seeing here represents a preparatory phase to the movement. Specifically, in this study, we see postural muscles activated more than 50 milliseconds in advance of the prime move muscles. In this movement, we will also see a compensatory phase, where postural muscles are again activated after the arm has moved to further stabilize the body. The compensatory phase is another way of saying that we're seeing reactive balance processes. In the preparatory phase of a movement, we are seeing the tensioning of some parts of the kinematic chain and the relaxing of other parts. The specific pattern of tensioning and relaxing that we observe is adapted to the specifics of the planned movement. For example, if we compare the tasks of raising the arm versus the task of lowering the arm, we find that there's a significant change to which postural muscles are recruited, and to the order in which they're recruited. The take-home message of this research is that the muscle activity preceding a voluntary movement appears to depend upon the demands of both postural control and voluntary movement. Postural control refers to the task of maintaining a stable, task-relevant body orientation. Voluntary movement refers to the task-appropriate transportation of the body from one posture to another. Earlier we discussed the flexibility and adaptability of reactive balance. Proactive balance has similar characteristics. As with reactive balance, proactive balance does not involve rigidly stereotyped responses. In other words, proactive balance control is adapted to both the postural affordances of the body and the environment, as well as to the demands of the task. You may not have come across the word affordances before, but you will end up seeing it a few times throughout the semester. Affordances refer to possibilities for action. And when you see the word affordances, you can just simply replace it with the phrase possibilities for action. If there is a railing in front of me, then we can say that the railing affords grabbing onto in order to stop myself from falling. In other words, the railing has the affordance or possibility for action of being graspable and of stabilizing balance. Let's look at an example where we can see the adaptability of both reactive and proactive balance. In this experiment, Cordo and Nashner had participants take hold of a handle that was positioned in front of them. This handle could be moved by the experimenter. Participants had to perform one of two tasks. They either had to resist the pull of the handle when the handle was moved, or they had to not resist the pull and allow their arm to be moved. Next, the experiment was performed in one of two ways. Either the task was performed while standing upright, or alternatively it was performed while the participant stood up while leaning their chest into a bar attached to the ground. In the figure on the right, we can see this second condition. The participant is resting their chest on the blue bar. The blue bar has the effect of bracing the shoulder. If the body is pulled forward, the contact of the chest with the bar will stop the body from swaying forwards. Given our current goal of understanding how the control of balance is adapted to the context in which that balance control occurs, we can think of this experiment in general terms. First, we're looking to see if the organization of reactive balance that we're looking at here can be adapted to changing task demands. Next, we're looking to see whether a change in the affordances of the environment will change the organization of reactive balance. Here we see the EMG time series for the biceps brachii and the gastrocnemius. Here we see that when the participant is given the instruction to resist the pull of the bar, that they recruit the gastrocnemius in order to stabilize balance, and they recruit the biceps in order to counter the pull of the bar. When the participant is given the alternate instruction to not resist the pull, we see a completely different response. What we see is no activity in either muscle. In simple terms, we see that a change in the task reorganizes the reactive response to the pull of the bar. Now let's look to see what happens in a condition where we brace the shoulder. Here we see that the gastrocnemius is not recruited when the task is to resist the pull. This is because it's not needed. The shoulder brace is keeping the body balanced. In simple terms, we see that a change in the affordances of the environment reorganizes the reactive response to the pull of the bar. Again, we're using to recap the term affordances. The bar coming up of the ground is providing the affordance of stabilizing the body. It's providing the possibility for action of an increased postural stability. Now let's look at the same task in the context of proactive balance. In this variant of the experiment, the participant is given the task of pulling on the handle after they hear a tone. Here the subject is organizing a voluntary movement. This time we have the shoulder-braced condition on the left. Following the auditory tone that signals to start pulling on the bar, we get a clear activation of the biceps. And we also get almost no activation of the gastrocnemius. As before, this is the most adaptive response. The gastrocnemius is not being recruited to stabilize posture when it's not needed. Now, when we look on the right-hand side, we see the EMG time series for the non-braced condition. Here we see activation of the gastrocnemius. This acts to generate a force that counteracts the anticipated perturbation. In summary, what we're seeing here is that when an external support stabilizes the body, anticipatory postural muscle activity does not occur. The general implication here is that muscle activity reflects the affordances of the situation. So, to recap on the concept of affordances, the bar is acting as a brace to posture. So the bar is offering a possibility for action. It's offering a possibility for stabilizing the body. One last thing that you should notice in this data is that the activity of the gastrocnemius in the not braced condition started well before the biceps had even started to build up a pulling force on the handle. The general implication of this observation is that the order of muscle recruitment is task-specific. Given that the task is to pull on the handle while maintaining an upright stance, we observe that a stable postural base for performing the action is first created, and then a voluntary movement is initiated. Let's look at one last example of how proactive balance is adapted to the context in which it's performed. Here we're going to compare the task of raising your arm while seated to the task of raising your arm while standing. Here we see the EMG time series for neck, trunk, and leg muscles. The main thing to notice here is that when the task is performed while standing, you see the hamstrings being recruited in order to stabilize the body. In contrast, as soon as the task is being performed while seated, this activity is no longer functional and is no longer present. In this example, we see that the anticipatory postural response is adapted to the demands of the current environment. In this lecture, we looked at reactive balance and anticipatory balance. Together with our study of steady-state balance in the last lecture, we now have a reasonable understanding of the different types of postural tasks that go into the ability of balancing the body. Our focus so far has almost entirely been upon understanding the motor constraints on balance. It's been upon understanding how the muscles and joints of the body are organized to move and act in a way that maintains a stable balance. Next lecture, we'll start looking at the perceptual and cognitive constraints upon balance.